I would also say that the chat box is disabled, but at the end of the talk, it will be enabled so that you can post any questions you may have for the speaker in the chat box at the end of the talk. So my name is Ian Sanders, and it's my great pleasure to welcome our speaker on the occasion of the 4th Ed Scott Memorial Lecture. That is Professor Don Brownlee. His talk is entitled "The Diverse Rocky Materials That Formed Comets." Don Brownlee is a professor of astronomy at the University of Washington in Seattle. He graduated from Berkeley in 1965 with a degree in electrical engineering, but quickly switched to astronomy for his PhD, which was at the University of Washington. Don has spent his entire career collecting and analyzing meteoritic materials from space, from the stratosphere, from polar regions, and from abyssal sediments in our oceans. In recognition of the outstanding caliber of his research, he received the Meteoritical Society Leonard Medal in 1996. Don was the principal investigator of the NASA Stardust mission, which returned the only laboratory samples that are known to be from a comet that formed at the edge of the solar system. That mission was launched back in 1999, and the samples were returned in 2006. Although the Stardust mission happened some 20 years ago, its findings still remain of key importance for our understanding of the origin of the solar system. A review of those findings is timely. So without further ado, I will hand over to Don.
Thank you very much. And if I can get my slides going here. Let's see. Is that full screen for everybody?
Yes, I can see that as full screen here.
Okay. Okay. Well, anyway, I would like to start off by saying it's a real thrill to give this talk in Ed Scott's name. Ed was just a terrific guy, and he was very interested in what I'm going to talk about today. And I always thought of Ed as a terrific source of information. Anytime I had some really gnarly meteoritical question, I would talk to Ed, and he would always have a very sensible explanation. Anyway, I'm going to talk about diverse rocky materials that form comets. These are results of the Stardust mission, which was the first sample returned from a primitive body. And the Stardust mission history, I'll go into a little bit. I'm trying to get my screen cleaned up here. The interesting thing about the history of the Stardust mission was that it started with Jeff Briggs from NASA headquarters called and said, "Hey, we have a spacecraft called IC3, which is in space. It can go to Halley and fly by at 70 kilometers a second and bring back dust. Can you do anything with it?" So Peter Sue at JPL and I feverishly worked for months on this. We used electron beam capture, electron beam weapon techniques, and variety of things, and decided that no, you couldn't do anything with a random spacecraft that went past the comet and was cratered by it. But it led to the idea of having a sample return we called HER, Halley Earth Return, which would go to Halley's comet and use capture cells to collect vaporized dust impacts. We collect them atom by atom and analyze them when they come back. This didn't happen. There was no U.S. Halley mission. But Peter Sue was very intrigued by this and was sure that intact capture was possible. There was some way to capture high-speed comet particles and bring them back to Earth. Most people thought this was crazy, but turned out that it is possible. And this had to do with a fabulous material called silica aerogel, which is like some people call it frozen smoke. Anyway, we were selected as the 4th discovery mission, and low cost and opened the door to future sample returns. It was interesting. So we knew that we could collect glass spheres and olivine at kilometer per second speeds, but we didn't know whether it was possible to collect actual cometary samples. And so there was a humongous question mark whether this was a folly or a good idea. Let's see. So pre-mission expectations for a comet sample return. Astronomers basically believed that comets formed in isolation from the hot disk material in the early solar system, and that comets were made out of presolar interstellar grains. Findings: we found out just the opposite, that at least for particles larger than 2 microns from the comet, that essentially all of them formed at incandescent temperatures, and that isotopically anomalous presolar grains were probably rare, less than 1%. The importance of this mission, however, was it provided unique samples of a small body that was never wet and spent most of its time beyond the orbit of Neptune. And we believe, until proven otherwise, that the samples we collected are probably representative of early nebular solids that existed beyond the snow line in the early solar system. A really surprising result was that the comets that we sampled are like Puget Sound beaches. There's a picture of rocks on a Puget Sound beach, and the rocks are diverse ancient rocks that formed somewhere else. They're relics, and they're unrelated to the geological setting that they're in, but they formed in many different environments. Well, comets are a similar thing. They're collections of a variety of things that formed elsewhere and then got together in the comet forming region. So comets and asteroids. It's interesting. There's probably a continuum surely a continuum between comets and asteroids, but in some ways, comets do differ very clearly from asteroids. You can take a 3rd grader and show them a bunch of pictures of comets that have been taken with spacecraft and a bunch of asteroids, and they can absolutely identify just from the image alone what is a comet and what is an asteroid. Is because the surfaces of comets are young and they're rapidly evolving because of sublimation. The surface of comets is greatly shaped by sublimation process, something that does not happen on typical asteroids. So it's interesting to compare Comet Wild 2, which we went to on the left here, with Ryugu, which is visited by Hayabusa 2. We both have samples from these things. And they're both similar to carbonaceous chondrites in many ways, but they are drastically different from each other in the sense that nearly all of the materials in Ryugu formed or transferred or transformed inside Ryugu. I mean, the samples are fabulous, they're wonderful from information about the early solar system. However, the majority of the things inside Ryugu formed inside that body. And these included things like smectite, serpentine, dolomite, magnetite, sulfides, phosphides, and phosphates. And anhydrous, which were the original silicates, are very, very rare. In contrast, the Comet Wild 2 that we sampled, at least for particles larger than about 2 microns, is dominated by silicates that formed at high temperature environments, at incandescent temperatures, and these are not environments where the famous ices and organics in comets could have had existed. By the way, most of the mass in comets is not organics and ice. It's in rock. So these are rocky bodies with some ice. These were anhydrous, and they had, because they never had pressure and temperatures high enough to melt ice. There was ice there, but it was lost by sublimation, not by melting. And the components in the comet, instead of being made inside the comet, were made from distant sources or with a range of properties. Okay, this is a picture of a bunch of 100 micron sized grains from Ryugu. And we actually, in our lab, we worked on 100 of these. And it was astounding to me that every single particle like this that we worked on was the same. It was the same collection of smectite, serpentine, dolomite, magnetite, sulfides, phosphates, and phosphides and phosphates. This is really amazing. And I had the feeling that if you gave me a single 50 micron particle from Ryugu, I could say, well, this looks like it's from Ryugu because of its content. And you cannot do that with a comet or even an interplanetary dust particle because there's just too much variety because they're mixing from many different places. Okay, from the comet sample that we returned, we did find presolar interstellar grains, but they were really rare, about 1,000 parts per million. And here's a plot made by Scott Messenger of interplanetary dust on the right and meteorites here on the left. And you see that the Cometville 2 is similar in terms of isotopically anomalous presolar grain contents to many IDPs, but it is actually much higher than most meteorites. You see Astro 094 down here is only 200 parts per million, which is a lot less than Cometville 2. So they're rare, much less than expected. The expectation was that it was 100%, but they're more abundant than in chondrites. Okay, before the Stardust mission, which was given the name Stardust because it was thought comets were made out of interstellar grains, comets were known to be dirty snowballs compared to interstellar grains. However, the astronomical data was a little odd. In the upper left-hand corner here is the infrared spectrum from SIO stretched, the so-called famous silicate feature at about 10 microns. So the diffuse interstellar medium silicates has this rather sharp profile, and that's associated with amorphous silicate materials. However, the same spectra from comets and also from young stellar disk around young stars shows a much different profile. It shows fine structure to the presence of minerals, olivine and pyroxene at 11.2 microns and a little over 9 microns. So this was interesting. So how can a comet be made out of interstellar grains if its infrared spectrum of its silicates is different from the interstellar medium, space between the stars? Well, the astronomer view of this was that the minerals seen in the disks and in comets was due to low temperature annealing. This is incorrect. From the sample we collected, none of the stuff we see really clearly has a signature forming at low temperature, but at high temperatures like chondrule formation processes. Okay, most presolar grains that were found in the comet sample were found in craters. Our main collection medium was silica aerogel, but it was held. The aerogel was like ice cubes held in an aluminum frame. And it turns out the craters were the best places to look for presolar grains because the material was highly concentrated in the liners of these impact craters. And this is upper right-hand corner is an interstellar, a presolar grain from Frank Stauderman in 2008. There were quite a number of ones found in the aluminum. There was one actually only one so far that's been found in the aerogel, and this was a silicon carbide grain, about a half a micron in size. You can see this isotopic map on the upper right, and it's a diffraction pattern. It's from a C3 beta cubic polytype on the upper left. So the Stardust mission collected dust that came from a comet, and this is dust that was ejected from active jets. We could see the jets. You can see the picture of the comet here with the jets superimposed on it. The jets are gas escaping the comet because of sublimation from subsurface regions, which have contained volatiles since the formation of the sun and the planets. And presumably this stuff liberated constantly at a rate of 20 tons per day is driven is released from things that have been frozen for the age of the solar system. The comet we went to, Wilt 2, is a very interesting comet. It was only captured into its present orbit in 1974 when it did a close flyby of Jupiter and changed its most distant part of its orbit from out by Uranus to now it's in an orbit that goes basically from Jupiter to a little bit further from the sun than Mars. Anyway, we collected particles by impact into this aerogel, silica aerogel, and so you can think of a track. A particle comes in from the top here. It comes in. The smaller particles don't go as deeply into the aerogel, and they're stopped in what we call the bulb region. And the larger particles penetrate all the way down to the tips. And what I'm going to talk about mostly today is the things that are found in the bottom of the tracks, particles larger than 2 microns, and these are well preserved. Noguchi et al. Doing experiments predicted that particles that are captured down at the bottom are not heated above 300 degrees centigrade, just 2 microns below their surface. The time scale for this capture is really quick. A particle at this speed passes its own diameter in a billionth of a second. And the time scale of interaction with the aerogel is on the picosecond time scale. So the thermal wave does not penetrate very fast, very deep in particles. Unfortunately, we know a lot about particles at the bottom, the ones larger than 2 microns. We know very little about the mass of material up in the bulb region, the submicron material. Okay, so here's just pictures of 3 tracks in aerogel particle coming in from the left. The top track is what happens when you have a very strong particle that doesn't come apart. The middle track is a particle that's coming in, and it's broken into major fragments, which are numbered on the right. And this could be like a chondrule fragment that was fractured somehow, had fractures in it before it hit, and they just separated. The ram pressures on particles entering the aerogel is actually very low, so you're not having sharp, hard shock effects on the grain to fracture them. It's a kind of a soft capture, even though it's occurring on very short time scale. And the bottom, which is common for the biggest particles, is the weakest material, and a large amount of the mass is in the bulb region on the left, and those are the smallest particles. This is an interesting track. The little dot on the far right is a sulfide. The little black dot between the sulfide and the main bulb is a calcium aluminum inclusion. And a little bit to the left of that, at the bottom of the bulb, is a presolar grain, silicon carbide grain, anyway. So hypervelocity capture is a miracle, really. I mean, it's going into silica aerogel, which is made out of sort of 30 angstrom size silica, solid silica particles in something that's only a few times denser than air, and superlative material. But there's a miracle that goes on in at least some fraction of the particles that are larger than a few microns develop a cocoon around them of compressed aerogel. Here's a particle. The circles and squares are areas that are triggered for analysis, for isotope analysis at Wisconsin. But you can see this cocoon around the particle. That's solid compressed aerogel, which is clearly protecting the material. This is an olivine grain, and the two white dots on the left are nickel iron metal grains. We'll see more of stuff like that. And the expectation is the particles below 2 microns from the surface are not heated above 300 C, at least during their deceleration phase. Most common particles larger than 2 microns appear to be chondrule fragments, and I'm going to just show a couple of these. So this is olivine and pyroxene and spinel. The K is camosite, and the glass is chondrule glass, basically. This is the first one that was studied in detail in Gozenzama. It's a type 1 chondrule. It has relic O16 rich olivine in it. It's amazing. So the main particle is made out of olivine and pyroxene, and there are also metal beads in it, nickel iron metal beads. But the two big olivine grains, A and B, have the same elemental composition, the same iron content, but they differ in their oxygen isotopes. So A is very O16 rich. You see, it's way down by the lower left, which is the composition of the sun, and that's something that predates the other materials that form. It's a relic olivine grain, and it's common for these what we believe are chondrule fragments in VIL2 to contain relic materials that are O16 rich. And anyway, here's just another one. I'll go through a bunch of these. Again, these are olivine grains. You can see the glass. Amazingly enough, the glass in every case that we've looked at is pristine. It's not converted to phyllosilicates. So this stuff has never been in contact with water, which instantly develops phyllosilicates. This is the largest one we found. We worked on this just last year. It's 60 microns across. It's dominated by FO60 olivine, so it's a pretty iron rich. There's little blades of augite, albitic composition glass, spinel, and around the fringes of it are chondritic fines, the stuff that normally ends up stuck up in the bulb, but those little vesicular melted stuff of that on the surface. And again, a really important thing is that there are no phyllosilicates in the glass. So this is a very pristine 3.0 type meteorite parent bodies situation. There's been no contact with water inside the parent body. So the isotopes, most of the isotope stuff I'm gonna show was done by Noriko Kita and her group. at Wisconsin. And this shows the heterogeneous oxygen isotopes, relic domain of cap delta 017 around -7 per mil, while others are up near the special fractionation line. This is the 60 micron chondrule on the left, and on the right is Gozenzama. The first one of these things was the work done on the right. But you can see the difference in composition. One is FO 60 something, and the other one is FO 95. So these are quite different chondrule fragments produced in states of quite different oxidation in environments. One is iron rich and one is iron poor. So the big, we worked a lot on track 227, which is the largest track that I think anyone has worked on the mission. And there was the 60 micron particle called TP4 on the upper right, but there were also a variety of other things that are fairly large size and were found in there. And they're also called terminal particles because of their size. Each has a little track in the bottom of the main track, and they're all different. They have different oxidized isotopic composition, different mineralogy, and different iron content of their olivine, as you can see in this next slide. So the TP 1, 2, 3, and 4, and this is the horizontal axis of this is the magnesium number, and you see they're really quite different, going from about FO 60 to FO 97 or so for TP3. One astounding aspect of the cometary olivine is the rather flat distribution of the magnesium number. So the iron content of the olivine, instead of being spiked at forsterite, pure magnesium olivine, and with a tail going out at higher values, is, compared to most other meteorites, is pretty flat, as shown in the histogram in the lower right hand part here. Okay, we can group the particles from this track into various groups, and I'm just going to mention one, which is very interesting, that what we call group 1, and these are ones with magnesium numbers between 52 and 55. So these are very, very iron-rich grains, presumably formed under very oxidizing conditions. But look where their isotopes plot. They're plotted above the terrestrial fractionation line in an area where there's no really comparable body. There is some overlap with iron poor CB chondrules, but not the iron rich ones. So there are really no comparable objects, an unknown source. And yet we found this in this limited sample we have of just a couple, hundreds of comet grains. It's fantastic to be able to do this. These are just for fun. These are from some 4 other unusual fragments and from this this track. On the upper left is pure forsterite, FO 100. There's no trace elements, at least that we can see in the TEM. To the right of that is an FO 86 that has a forsteritic core, and both of these are cap delta -23, like the sun. And on the right is gossurite, a very refractory material, and the upper top is a little dot up there, and that's refractory inclusion, refractory metal nugget, which we occasionally see. On the lower left is an intriguing thing. It's about FO100 olivine with iron poor, silica-rich, and calcium and aluminum-rich glass in between. And this is normally this would be considered a crystalline material. With the TEM, we can see that it's not. It's nice olivine crystals with glass in between it on an extremely small submicron scale. Built-to chondrules seem to differ in part from chondrite chondrules and microchondrules, and we don't think that you can make these by smash formed chondrules where you have collisions of liquid bodies because of the presence of the relic grains in it, which are made from an earlier generation of O16 rich material. So olivine is probably the most common mineral in the universe. It's very common in the comet sample that we work on. Most of the silicates are olivine and pyroxene. And so we can compare them in various ways. One is just looking at the histogram of the iron content. And I mentioned previously that a big difference between the comet and most meteorites is that we see such a huge range in iron contents of the olivine, going from zilch to about FO50 or even more, which requires more and more oxidizing conditions to have that much iron put in the olivine. The on the right is a plot of the manganese, the iron ratio. AMU is atomic formula units. But anyway, this is the data compared to ordinary chondrites and CO chondrites. And I'm going to show this a little differently on the next slide. But this plot can be is evidence that VILT2 has abundant carbonaceous chondrite materials, but also things related to similar to what's found in ordinary chondrites. So the next slide here is kind of an expansion of this. On the left is the manganese and iron plot for olivine from ordinary chondrites and CO chondrites. And you see there's a high correlation between manganese and iron because manganese is substituting, Mn2+ is substituting for Fe2+. And the ordinary chondrites are higher than the CO, which is about the solar ratio for manganese and iron, because a major fraction of the iron is actually in metal, which the manganese cannot fit into. For CR chondrites, in many ways, the materials in comet VILT2 are similar to CRs. And CR pattern for manganese and iron is intermediate between CO and OC. The comet data, and we actually have two sources of data here. One is the actual VILT2 measurements, and also red squares are from a comet, what we believe is a cometary interplanetary dust particle. And they both, you see, they have fantastic scatter. There's no tendency at all to see any correlation. And it also fills areas that are not seen to the two plots to the left, so-called forbidden triangle. And so this is an argument that the materials in the comet came from a diverse range of environments, and so the VILT2 olivine is not like any meteorite class in terms of manganese to iron correlation, and that VILT2 vorous olivine come from numerous sources. Okay. So we also have an interesting clue from low calcium pyroxene, and Dave Josvik has done a lot of interesting work on that. And these are plots of Vil2 cluster IDP, interplanetary dust particle, and meteorites on the left. So the chromium aluminum in low calcium pyroxene from chondrules plots in that blue region on the far left. And then generally that's a good agreement with the Vil2 and the cometary IDP. So we believe that the high chromium and high aluminum is indicative of a chondrule origin. Now in chondrites, there's these red points on the lower left of the left-hand plot are low because of heating, because of parent body heating. So chromium has diffused out of low calcium pyroxene, and aluminum has gone out because it's formed plagioclase. We see this similar pattern in the comet, but we think it's for different reasons. It's not due to heating. These are actually condensates, and because the unequilibrated manganese, iron, and other factors indicate that these samples were not heated, like the high metamorphic grade chondrites. Okay. So the relations of chondrules to oxygen isotopes. Here's our oxygen isotope data, and there's on the right there's an overall weak correlation between magnesium number and cap delta 017. There are common O16 rich relics, which are in the lower part of these of this plot on the right. Going to the plot on the left, the traditional 3 isotope plot, most of the points are on the PCM line and overlap with CR chondrules and slightly overlap with ordinary chondrites and CH and CB chondrules. There's the upper right again shows this cap delta 017 increase with increasing iron in the olivine or decreasing magnesium number. And it goes from about -3 per mil to about +1 per mil. This implies that some of the materials formed in very oxidizing conditions with presumably with a fair amount of vaporized ice or vaporized silicates in order to produce the oxidizing conditions. Here's the data from many particles from a single track that we have. And these are all grains that are larger than 5 microns in size. And we've got over 100 points now. And you can see again, there is a positive slope. And there's this interesting thing at the far right-hand side, the iron rich, the magnesium, high magnesium number, low magnesium number, high iron, which is actually with cap delta positive values, that means above the terrestrial fractionation line. So an exciting part of the analysis has been the data that's been able to be obtained from aluminum-26, magnesium-26 chronology. This is very, very difficult because the particles are small and because there aren't many large regions that have a high aluminum-magnesium ratio. Nonetheless, a variety of particles have been analyzed, and there's been no resolvable excess magnesium-26. And so all we've been able to do is set upper limits on the initial aluminum-26-27 ratio. And we'll go through this. The latest data has been done by Ming Zhang on the little sample called Perixie, and it's a 30 micron particle. It's very interesting. The best results so far. And the lower right-hand particle is a new particle that we just recently found. It's a phyllosilicates rich, and it will also provide more interesting data on aluminum-26. But anyway, this is the best data we have. No resolvable excess, even with improved precisions on that grain. And the origin of the silicates is very interesting. This is the upper limits obtained, implying the low initial 26-27 ratio of less than 2 times 10 to the minus 6, not 5 times 10 to the minus 5, but less than 2 times 10 to the minus 6. And if you assume a uniform aluminum-26 distribution in the early solar system, you can get an age. The minimum age is greater than 3.6 million years, which is very late. And in terms of comparison with chondrites, it's different than chondrules from ordinary chondrites, from carbonaceous chondrites, and it's the best match with CR. But then there are some other matches for that. So the implication, if aluminum-26 was uniform, that these things formed, the cometary chondrules formed late. It's also possible that there are other solutions to this. One idea from Larson et al. Is that these things in the solar system that are aluminum-26 poor or devoid, such as fun inclusions and plaque inclusions, could have happened because of a batch of material, a bunch of interstellar material was accreted into the inner part of the disk, early solar system disk, late. And it was old enough that its aluminum-26 had already been decayed. So it's been an age of like 10 million years. And so it's basically aluminum-26 dead. And so you can see this. Let me get my pointer isn't showing up, but you can see that this top trajectory here is aluminum-26 poor. That would be a late occluded cloud, material that got vaporized, reformed materials, and then ejected to the edge of the disk, but it was aluminum-26 dead. Okay. Okay, so one of the most exciting things we found early on was calcium aluminum inclusions. The first one we found was INTI, which is a very large particle, about 25 microns, and it was made out of, it was a collection of nodules that are just micron size. And you see on the right, and it had the isotope composition was the same as the sun. So it was really exciting. So, you know, Stardust and the Genesis mission were kind of twin missions. One went to the sun, and the other went to the edge of the solar system and collected materials. And it was quite astounding to see that we found the same oxygen composition in both places. We found solar isotope compositions that O16 rich in INTI as Genesis found from the sun by measuring solar wind. Anyway, we found these classic CAI materials, and spinel, facite, grossmanite, galenite, and anorthite, and some things that we were a little bit surprising right here. Titanium vanadium nitride, which I'll show some more pictures of shortly. So these have nodular structures. They're microns sizes. Each is rimmed with a sequence of high temperature minerals. And at some time and place, these micron nodules were a dominant solar system solid. These are just some maps of the built to nodules. These are really small ones, but you can see their diopside around anerothite with spinel and in the core, and a little green dot in the lower right-hand corner and with pointed to by arrows is osmonite, which is titanium nitride. And the titanium nitride is a very interesting thing. Who would have expected to see that in a comet? It's an extremely high temperature condensate. It forms at about 1600 K. And in some regions, it was the first condensate. This is work by Denton Abel on the left. So it condenses from vapor and special conditions, very high temperatures as a first condensate, but only when the carbon to oxygen ratio in the gas is about twice solar. Solar value is about 0.55. And here's a picture of the EELS spectrum of it, and you can see there are 3 or 4 of the osmonites really in this one little picture. That was a real thrill. So the CIIs, we found a number of them in the comet. Most of them are smaller than the NT, but this is a plot of the frequency of properties, and the ones that we found in the comet, they all have spinel, grossite, and anerothite. They don't contain corundum or hibonite. We did see perovskite and melite, but it's rare. So from that and also things like the refractory metal nuggets, we think that these are sort of low temperature CAIs formed at the lower temperature range. So this neat similar nodules are of course found in meteorites. Here's a great picture of given to us by Sasha Krot of a large CAI that contains 10 million of these little micron-sized nodules. So there were some early nebular environments that were dominated by these REMS nodules. Among other fascinating things found are lime forest. These were first not pointed out by Wolfgang Klock. They were first found in interplanetary dust particles. There was a highly enhanced manganese to iron in a forest-duritic thing thought to be condensates, low iron, manganese enriched. One of the intriguing things that were unique things that were found in IDP, interplanetary dust particles, and in Built 2 are things called cool assemblages. That's composed of cosmochloric high calcium pyroxene and iron-rich olivine. I'll just show a couple pictures, but these are only observed in Stardust and IDPs. As far as we know, they are not seen in chondrites. We haven't seen them. This is a picture of a particle that has a KO oxide is a cosmochloric oxide, and here's a spectra on the bottom. You can see it's oops, sorry about that. It's amazing 6% sodium oxide and 13% chromium oxide in this mixture with acetite and penlandite and so forth. It's some unusual cool grain. So many of these cool grains are equilibrated but they're solid rocks. Okay, the most of the mass we believe that hit our spacecraft and was collected is submicron matrix, the dominant mass, and we don't know what it is. Optically, consists of blobs up to 50 microns in size, as seen on the left here. On the right is a TEM picture taken by Brownlee and Ishii. It's a mixture of silica glass with extra silica from melted aerogel, which melts at about 1700 centigrade, and two immiscible phases, beads of sulfide and nickel iron metal. And we don't know what it is. It's what was it before it melted? It's chondritic elemental composition at the micron scale, and it has these little sulfides and metal, which are just immiscible. One possibility, in my opinion, is a likely possibility that there are things called gems, with a glass with embedded metal and sulfide. These are found in interplanetary dust, which anhydrous interplanetary dust, which are probably the most primitive meteoritic materials. Another thing that could have been was phyllosilicates, because those are all fine grain and can have elemental compositions similar to the chondritic bulk compositions. But those are two things. Other than that, what else could be fine grained enough to melt and have chondritic composition at the micron scale? It's just a mystery, and it's depressing that we haven't been able to figure out what the stuff, the matrix was after 2 decades of working on it. Okay, one direct way to see what the little particles are is to look at the smallest particles. Here's a size distribution of particles that hit our spacecraft, and there's on the little craters on the right are craters made by the smallest particles, which are submicron in size, in aluminum. And there's been interesting work in analyzing the liner at the bottom of these. The fib use focused ion beam to cut sections through these tiny submicron craters, and you can analyze the composition. There's an elemental composition on there's an EDX spectrum on the bottom, and that's a chondritic spectrum, solar relative peak value. So this was whatever made this crater had the same composition as the sun for rock forming elements. I'll go on. So wrapping things up here, a significant number of well-preserved solid comet particles larger than 2 microns have been analyzed in detail. We still don't know much about the fines, but we know a lot about the coarser particles. And this is cometary ground truth that must be considered for anybody modeling what's happening in the outer part of the solar system. The particles we collected are probably representative of the 2 micron solid particles at the edge of the solar system. My guess is that all comets have the same mix of rocky materials in them and are similar to Wilt-2. The similarity of the Wilt-2 sample to hundreds of anhydrous interplanetary dust particles that people have worked on, suggested Wilt-2 is a typical small comet. It's not a weird comet. It's a typical stuff. The abundance of chondrule fragments in Wilt-2 implies that chondrule formation processes form most of the greater than 2 micron rocky solids, and these high temperature igneous environments could not possibly have formed in the same environments where ice and organics formed. The big question is, where did these igneous materials form? In the inner solar system, where things were hot and dense, or in the outer solar system, where things are less hot and less dense, but you have giant planets forming with quite spectacular environmental situations around them. And the comet samples, were they ever inside other parent bodies? That we see fragments of things that previously existed. Were they in parent bodies? I don't think so, because we don't see metamorphic heating on these, at least not impressive metamorphic heating. And then if they formed in hot places, how did they reach the cold places where the ice and organics could form? So larger than 2 micron grains contains polyphase fragments formed in diverse environments. Most isolated silicates are likely to be chondrule fragments. Some isolated silicates are almost surely condensates, and related to AOA fragments, amoeboid olivine aggregates. And these include things like lime, olivine, and high O16 rich grains. Refractory grains are most similar to fine grain CAIs. We also find a lot of sulfides, pyrrhotite, and penlandite. And rare occurrence, there are rare occurrences of secondary phases. This is magnetite and even cubonite, but these are generally rare and not found in typical tracks. So these could be fragments from other altered bodies. I mean, there are small comets that form, and there are big comets. If you bust up Pluto, you have lots of secondary phases inside. But the fact is that we don't find phyllosilicates, carbonates, or classic CI magnetite forms, which is a very strong argument that there was no alteration on the parent body, on the cometary parent bodies. So varied environments needed to make build 2 rocky solids. Type 1 chondrules, iron poor. Type 2 chondrules, iron rich, requires an enhanced oxygen and hydrogen above the solar value, and this can be caused by vaporization of silicates and or ice. Ferrous olivine with positive cap delta O17, the positive form above the terrestrial fractionation line. Aluminum chondrules, aluminum-rich chondrules, lime olivine, AOA, pure forestite, pure histite, and CIs are all O16 rich. There's an enormous number of O16 rich materials that have been found in our really quite limited collection of cometary materials. Osbornite is quite an exotic kind of material, and it seems to be quite prevalent in the refractory comets. We've never seen it, however, in an olivine or a pyroxene. And presolar isotopically anomalous grains. The numbers we have for the presolar grain content is a lower limit. Surely it was higher than estimated and degraded by the capture processes. So how do the chondrite building materials reach the comet accretion phase? I mean, it was shocking to everybody to see a CAI in the coldest body of the solar system that we collected samples from. But Frank Hsu actually predicted that CAIs and chondrules would be found in comets because they were ejected by the X-wind. Now, some people, Steve Desch, has been strongly criticized the X-wind model as a transport, but nonetheless, there are outflows of disks which can distribute grains. They don't have to come from the X-wind, but they can come from other sources. But if you transport radially large distances, there are 2 possibilities. One is in the disk, and the other is above or below the disk by a ballistic transport. And so how did they go? Well, we don't know. Did they these igneous materials form in the outer solar system or the inner solar system? In the outer solar system, they could have formed by shocks or giant planet embryo formation or collisions of molten bodies. Bridges et al. Suggested they were performed by shocks. It's also, it's very interesting. The data from Ryugu opened a lot of interesting insight into this. Unfortunately, we can't search the dichotomy or where the comet fits into the dichotomy of isotopes in the solar system, because our samples are unfortunately still too small. We need a bucket of the of this stuff. But the Ryugu analysis for iron and nickel showed that there is sort of a dichotomy of NC and CC materials. There was the Ryugu and the CI type things seem to be like a third category of materials. And so this led to suggestions that that Ryugu actually accreted out of material that was the top paper here by Hop et al. Out in the Uranus and Neptune region. And a more recent paper by Spitzer et al., which is based on the nickel isotopes, has them forming more in the inner solar system. I mean, not in the inner solar system, but out in the sort of giant planets, Saturn, Neptune region. So at least in my mind, the whole business of large scale transport is really wide open now. And we went to a comet, which we know is formed with ice, and it's always been icy. But then there's a possibility that something like Ryugu, which is not an icy body, but it was an icy body at one time, may have also formed at great distance from the sun. So this comes down to issues like why small comets like Vil-2 and small asteroids like Ryugu may differ. Well, active comets retain near-surface ice and supervolatiles like CO, frozen CO, and the near-surface ice could not survive moderate heating. So it seems highly unlikely that any active comet was ever heated, at least on a global scale. Liquid water, which is common on asteroids, is really difficult to form inside small comets. And it's quite likely that all the comets that have been visited by spacecraft actually formed as small comets, not as bigger bodies that broke up, which is different than asteroids, because almost all the small asteroids are, in fact, fragments, including Ryugu, are of much larger objects, which, because of the environment they had to survive in for the age of the solar system, they got broken down into small pieces. So comets might have a broader sampling of disks of materials. Their accretion timescales might have been larger than the mixing timescales. So finally, I like to end up with this last picture of what truly primitive material is. So this is an interplanetary dust particle. It's not a Vil-2 sample, but this is what I think the Vil-2 samples are like. It's a mixture of fines and coarse materials. And this is interplanetary dust. It's about 10 microns in size. It contains a large amount of gems, glass, and embedded metal and sulfides, which are all submicron, and they're chondritic even at the micron scale. That's an instantite whisker, which grew from vapor phase. It grew to a whisker shape because it grew about 50 times faster in one direction than it did in the other. So, and then there are these large crystals, which are probably vapor phase grown also on the right-hand side. But truly primitive materials are really just porous aggregates of unequilibrated components. They're not homogeneous. They haven't had atoms diffusing from one grain to another. They were never wet because you couldn't have water. You didn't have high enough pressure and temperature to melt the ice that was had to be with them originally. They were never compacted because they weren't pounded by impacts. And they were not very strongly heated in the parent body because either the parent body was small or it didn't assemble until after aluminum 26 had already decayed. There's a name for this structure called ultraporous lithology, or UPL, mentioned by Matsumoto in 2019. So we have comet samples. We desperately, I really encourage everyone in listening to this to try to get a new comet sample where we collect at least a handful, if not a bucket full of material, because it's a fabulous source of information about what actually happened in the early solar system. But we also have interplanetary dust, and this is a picture of a 350 micron interplanetary dust particle, which contains thousands of grains. The biggest one, the elongated worm thing on the upper left, is 40 microns long and has an azotype grain. And this is a comet sample return. And this was collected U-2 airplane in the atmosphere. So additional sources of information. I've only covered a couple topics related to the Stardust mission in my talk. There are other things like bulk composition, carbon organics, and rare gases, which are all important. And here's a list of things that you might want to read if you want to learn more information about it. So anyway, this is the end of my talk, and we can apparently enter the chat session now, and I'll be happy to answer any questions that you have.
Well, Don, thank you very much for an absolutely splendid talk. I knew rather little about Stardust mission, and I'm ashamed to have to admit that, because there is such a wealth of information. I had not appreciated just what a wide range of different materials are all captured in these tiny grains that you've been able to analyze. So thank you. I say that on behalf of everyone, I think. And I open up the chat box for anyone with questions. Okay, so I see a question there from Diane Wooden, and it says, what is the fraction of material in stardust that are, sorry, my screen's just jumped. The fraction of materials in stardust that are CAI as opposed to other silicates.
We have the CAI fraction is a percent. We've said it's 2%, but I think it's more like more like 1%. The phyllosilicate, as far as I'm concerned, is 0. We haven't seen phyllosilicates. We have seen graphite. I mean, we have seen magnetite and cubonite, but we haven't seen phyllosilicates. And there have been numerous experiments of shooting phyllosilicates into aerogel at the 6 kilometers per second, and the expectation is the phyllosilicates, at least some of them should have survived.
Mm-hmm.
However, if the phyllosilicates were extremely finely grained, uh, they could have all been destroyed by the capture. I think this is highly unlikely. It's, people use the term very fine grained for phyllosilicates all the time, but they're not. The D species may be short, but they're like crumpled up piece of paper, and phyllosilicates usually have multi-micron regions of continuity. And we know a lot about phyllosilicates because in interplanetary dust, half the particles that we work on have phyllosilicates in them, and you can usually identify phyllosilicates presence even before you focus the microscope because of the distinctive patterns that they have.
Yeah, thank you. I think we'll move on to the next question here from Alan Rubin. He writes, chondrules likely formed locally throughout the nebula. The chondrules from carbonaceous chondrites formed in the outer solar system and likely were accreted by the neighboring accreting comets. The interesting problem is how the ordinary chondrite-like chondrules got there. And
Yeah.
I have the same puzzle in my mind too.
Well, it's also the CAIs. I mean, did the CAIs come from close to the sun, or is there some magic you can do to form those in the outer solar system? And we also see a lot of O16 rich material, and so if that has to do with radial effects in the disk, or I know people talk about having O16 rich materials because of photochemical things from UV from other stars, or from outside the sun. I don't know, but I think it is a big question, whether the stuff that we see in the comet, did it preferentially come from certain regions of the disk or all of the disk? I mean, my naive view of it came from the whole disk, and that's because I feel that way because early on we found CAIs. I mean, one of the second particle we worked on here in Seattle was Inti, which connected, most people connected with the sun.
Yeah. Okay. I'll move on down to the next question, if I may, which is from Richard Greenwood. And I'll mention, incidentally, that Richard is taking over from me as organizer of the Ed Scott lectures from next year. So you'll be seeing something of him. But what Richard asks or comments, he says, as a speculation, do you think comets are homogeneous or diverse like chondritic meteorites? Could there be distinct classes of comets? That's the question he asks.
That's an excellent question, and we know that comets are diverse based on their volatiles, and because we see different kinds of comets, and it's easy to imagine why comets would be diverse from the volatiles. However, for the rocky materials, which is the bulk of the mass of most comets, my guess is that they're all the same. I mean, if comets are a collection, a garbage can of what dust is flying around the solar system, you might expect that once you get beyond a certain radial distance in the solar system, that things would be the same. And we've worked at hundreds of interplanetary dust particles, which unfortunately each particle has its own history of atmospheric entry and blah 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 blah. But nonetheless, they do have these commonalities. None of them have 100% have interstellar, presolar interstellar grain at 100%, or even more than 1%. And so I think this incredible amount of flying around of nebular solid materials. So I didn't mention it all in the talk, but one really important thing that all the grains I talked about were solid. I did put the name solid usually in there, but I didn't emphasize it. But there's a difference between solid grains, like chondrules, and dust balls. And most of the things you see flying out of comet are dust balls. And so when people model it by whatever process, you got to think, what is a real grain, a mineral grain, or a solid material versus a dust ball. Dust balls are porous aggregates, and they're just clusters of miscellaneous things stuck together. But anyway, but my feeling is that once you go out a certain distance in the solar system, that there should be a similarity. I mean, the CRs are a big group. They're thought, some people think, form very far from the sun.
Yeah, well, yes, I must say it's just an amazing constraint on any model to have this very uniform stuff out there made of anhydrous bits and pieces that have come from a whole range of places, so it seems. Anyway, without me talking anymore, I just want to mention Richard Hurd's comment. I'll just read it out. He loves the analogy to beach pebbles, and I must say I agree wholeheartedly with that. I think that's a lovely picture you had at the beginning of your talk. But there's a question, one last question, and then we'll wrap up. It's a question from Qingzhu Yin, and he asks, Don, is there a way to tell if Ryugu is an altered comet-like material, or Ryugu is truly asteroidal and compositionally different from comets?
Yeah, I don't know. But my guess is there's a complete continuum between asteroids and comets. And Ryugu was an asteroid. I mean, was a comet, right? It had ice in it. It must have had a tail. It lost its water. So if I think the official definition of a comet is it has to have cometary activity that's observed. And there weren't any observers around to observe Ryugu when it was actually losing volatiles. So I think most of the Semi-Kona was a comet, right? It had aqueous alteration of glass in chondrules. It had to have ice in it at one time, and it melted and it lost it. So I think a lot of the meteorite parent bodies would have been considered comets and had cometary activity if there had been astronomers around 4.5 billion years ago to look at their tails. So it's a big issue of what's a comet and what's an asteroid. But
Well, I must say life would be very dull if there weren't a lot of unanswered questions. We'd all be out of work. Anyway, on that note, Don, thank you very much indeed. I thoroughly enjoyed it. I'm sure I'm speaking on behalf of all the people who were listening in. Thank you again for just a wonderful talk. Thank you.
Well, thank you for organizing this, and I wish Scott could have listened to it, because he was really interested in all our findings.
Absolutely. Thanks.